Thank you once again. And if there are any questions, please feel free to address in the Q&A box. So we'll move forward to the fifth speaker of this webinar, Andrew Patterson. Andrew is the Technical Director for Eurofins Environment Testing America in the Specialty Services Division. Capitalizing on his 20+ years of MS experience in the environmental lab, his focus at Eurofins has been the advancement of analytical techniques for the trace analysis of standard and emerging contaminants. We are very pleased to have Andrew Patterson speak on some of his work in a talk entitled Use of 13C labeled internal standards for accurate determination of 6-PPD quinone.
Thank you, Andrew. Okay, it looks like I'm sharing my screen. I can get a nod from you.
All's good. Thank you.
Named Andrew. Yeah. Hi. We're going to switch it back to the environmental realm. Really a little different than we've heard today. I've been glued to my laptop here. I think I'm very honored to be part of Isotope Day. So this is really cool. Today we're going to be talking about sort of the growth of the analysis of 6-PPD quinone. Really wouldn't be possible with the level that we need to get to without isotopes. That's why we're here. So in case everyone hasn't heard about this emerging contaminant, 6-PPD quinone, there was a lot of work done by the University of Washington, but also Washington State. Some of the state folks up in Washington, I think SQUIRP was involved. This was really a collaborative effort, but it was published back in December 2020 in Science. Ubiquitous tire rubber derived chemical induces acute mortality in coho salmon. That was the headline grabber. And we were really impressed by this work. It had to be bulletproof because of the nature of just the industries involved. And so the work is pretty amazing. And if someone hasn't had a chance to read that paper, I highly recommend it. 4 days later, we started with support. That's what we do as an analytical laboratory. This is great. All this amazing discovery work was done. How does the industry support it? And so we usually like to go out and start with purchasing some of the native compound. In this case, we couldn't do that. So you saw all these headlines and everything else going on. And some of the work that this summarizes some of the work that UW did. It was really pretty interesting because they took a preparative chromatography approach and isolated the toxic fraction. And so they, much like Mark Steiner was talking about, they had all these features. This was, there was about 2,000 features in this tire slurry, and they kept isolating it down until they found the fraction that was toxic to juvenile coho. And this is pretty amazing because in the environmental world, really it's rare that it's just one compound. We work a lot with PCBs and dioxins and pHs and PBDEs, and that's a whole group of compounds, 2, 3, 400, 600 with toxaphene or something like that. So the fact that we have just one compound to look at is pretty amazing. And they actually isolated this single compound, and it turns out to be 6-PPD quinone. And the trouble was that 6-PPD quinone isn't actually added to any products, but is in fact itself the product of ozonation of 6-PPD, the parent compound. So 6-PPD and 6-PPD quinone are definitely not the same thing. 6-PPD is added to tires along with a lot of other compounds to help stability, to achieve important federal safety standards. It's not the only compound that's added as an anti-ozonant, but this one happens to be toxic to salmon once it's oxidized. So this is added. I've learned more about tires than I thought I would, but this is added to tires in different proportions, whether it's the sidewall or the tread. But we're talking percent level. And then no matter if we have an internal combustion car or an electric car, we all have tires. So as we drive, this compound is actually doing what it's supposed to and protecting the rubber from ozone breakdown. Ground level ozone is a thing, and this compound does help protect it. So again, this compound is designed to be reactive and it is. The unfortunate truth is that the breakdown product, the ozonated product, the 6-PBD quinone, is then acutely toxic. First discovered to be acutely toxic to coho salmon, not as much with Chinook salmon or other salmonids, but it is. There's some papers that came out of Canada indicating that it is also toxic to some extent to rainbow trout. We've all got rainbow trout. Again, this compound does have a couple amines, which makes it sticky. That was the very first thing we found in the lab. And in fact, sort of the exciting part of this whole thing was we couldn't actually get a 6-PBD quinone native standard, much less an isotope, when this all started in early 2021. So there was talk of ozonating our own parent compound. We actually got our hands on a little bit of sort of this, we'll call it beta 6-PBD quinone from one of the universities, just so that we would have something to work with. And we were fortunate enough to be performing all the method development on a Q-TOF, on an LC Q-TOF, so that we could use exact mass to determine just what we were looking at. And really, I guess the best way to determine sort of the early method development is that we knew we were making decisions based on absolute area, whether it be for extraction solvent or for early attempts at solid phase extraction. But we really didn't have a good quantitative scheme for the whole thing. We knew that once the parent compound is very reactive, but we're having pretty good luck with the metabolite with 6-PBD quinone, both at ambient and at 4 degrees C. But again, this compound likes to stick to everything. It was kind of a headache to work with, but we were tasked with coming up with a method to support the research. So we did. Once we found the native, that was manufactured by, I think, a German vendor. It was great. So now we could do everything we wanted to with an external standard calibration, but we still needed an isotope. And so we said, okay, so just a little primer on isotope dilution. This is the heart of why we're talking today. We know we need to look for a compound in the environment, but we need to be able to quantitate that compound with certainty. And so a stable labeled mass, stable isotope of 6-PBD quinone was exactly what we needed. And so the idea behind isotope dilution is that you add your isotope to your sample, to your raw sample. And in this case, we were gearing up for a lot of storm waters, a lot of surface waters, pretty nasty stuff. So you add this to your sample beforehand. Your isotope follows whatever procedure you're doing. In this case, it's a solvent extraction followed by solid phase extraction, and then concentration down for analysis on LCM SMS. And so the great part about this, and this very high-tech drawing here, is that your analyte of interest will show up on one ion channel, and your internal standard will show up directly below it in retention time. And so whether it's a positive detection or a negative detection, the presence of your isotopes will signal that you had a successful extraction. So really, we tell clients, this is the gold standard for quantitation. We need this isotope, otherwise we won't be able to perform any loss correction. You're talking about matrices that are filled with, these are freeway runoff samples. Really, were some of the early samples, and they're filled with all sorts of detergents and surfactants and motor oil and anything else you can think of. And so, of course, we were going to encounter some loss in that extraction and cleanup process. But having an isotope present, the math allows for loss correction. So this is great. This is our whole bread and butter, where we want to be in the analytical laboratory, which is to deliver these data with confidence and be able to stand behind them. So we're off and running. But again, when everything starts out, there's always room for improvement. So the first isotope that came out was this D5 6-PBD quinone. That works okay. Under low pH conditions, you can have deuterium hydrogen substitution, and so again, deuterated standards are generally more economical, but they do come with some drawbacks, and the DH substitution is one of those. But it was the only thing we had. So this was a step in the right direction. We've worked with this standard a lot. It is a great product, but we're always looking to go from deuterateds to carbon-13 labeled when we can. CIL first came out with this 13C6 6-PBD quinone. Again, this is a little too close for comfort, only 1 AMU apart from the D5, so it's really tough to work with both the D5 and the 13C6. We could, but it's generally something we like a little more real estate in both between if we're using multiple isotopes in between each other. The nice thing was that we're very vocal to CIL, and we said, hey, look, we know this method isn't going anywhere. We know there's more and more papers on the subject, and really it was a couple of those Canadian papers talking about rainbow trout, where we said, hey, look, this emerging contaminant isn't going to be a flash in the pan. This is going to be something that's here for a long time, and we really need isotope support, multiple isotopes to be able to do what we want to do. And they listened, and they synthesized 13C12 6-PBD quinone. This is great. Now we've got a couple of different isotopes that we can quote unquote play with, and so to use 1633 lingo here, we're proposing to use the 13C12 6-PBD quinone as the extracted internal standard, or the EIS, and we're likely going to use the 13C6 6-PBD quinone as the non-extracted internal standard, or the NIS. And so this really is a concise suite. Talk about the perfect situation where we have one native, that's the 6-PBD quinone. We have an extracted internal standard, that's the 13C12. And then we have an NIS, or I guess some other people would say this is a recovery standard, if you're talking about something like 1613, or an injection standard. We, of course, like to have as many acronyms as possible to confuse the subject. But if you think about the 13C12 is going through the extraction, it's going to mimic everything the native compound does. And then at the end of the extraction and cleanup process, we're adding this NIS to be able to quantitate the recovery of our EIS. So a very concise suite of standards here. We shouldn't discount the D5 all the way. We're big here at Eurofins on working with passive samplers, and so the possibility that there is another isotope can lend itself for possible use as a tracer or a PRC, a performance or reference compound, when we're working with passive samplers. But again, this we went from not even having a native compound to having multiple sources of natives, which is great for needing a second source standard or an ICV. And then we have 3 isotopes to choose from. So we're very happy with how this turned out. So what do we do with that standard? So we take your sample. These are generally 250 ml aqueous samples. I have a slide on all the matrices that we've looked at. We're really in that exciting delineation phase where we're not only collecting samples, we have this method up and running right now out of the Sacramento lab. So we get your sample from the field, we spike in our internal standards, that's that 13C12 6-PBD quinone. We're using an SP extraction, and it's a fairly rugged, straight styrene dimethyl benzene SP extraction with a few unique wash steps incorporated. Again, this is a sticky compound. We did think about something like weak cation exchange, but the straight SDB seemed to work just fine. And again, we were lucky enough to have 3 LC Q-TOFs in Sacramento. So we started analyzing this on an LC Q-TOF until we better understood possible interferences. And once we were satisfied with how it was running on the LC Q-TOF, we did parallel samples between the LCMS and the LC Q-TOF. Again, and now that we have isotopes, we're able to do isotope dilution quantitation, which allows loss correction. And then we upload our data there. This is a pretty straightforward one because we just have one analyte of interest, but we don't use any algorithms to look for peaks. An actual human, no matter if it's a PFAS sample or PCB sample, a couple humans, in fact, review all those peaks and make sure that everything's in order. So what have we tested so far? So there is there is some interest for testing this compound in drinking water. I can tell you that we really haven't seen it in drinking water. I live next to a lake here in Northern California, and it's a pretty decent sized lake. And I actually got up to about a liter of sample. So we're talking detection limits down at 0.5 ppt, and we still had non-detects. So while this compound is in the environment, we're still learning where it is and isn't. A lot of questions coming up about influent and effluent. How do wastewater treatment plants deal with this compound? Where is it deficient, or at what point is it overwhelming the wastewater treatment plant processes? We still don't know that. I think that's an interesting topic. Soil sediment, we've definitely seen some roadway sludgy sediment samples come through. And those, again, the half-life, and I forgot to mention that earlier, I apologize. The half-life of 6 ppd to 6 ppd quinone in biologically active waters is something like 3 to 5 hours. So by the time a sample gets here, we're really not seeing any of the parent compound at all. We do monitor for it, but we're not seeing that reaction has carried through all the way. Wipe tests, this would be on some consumer products. You have consumer products listed at the bottom because the way to create 6 ppd quinone from 6 ppd is through increase of surface area. And so you could take a wipe sample and get one result. You could grind that product up and let some time pass, and you might get a different result. So we know that reusing recycled rubber is a really, really great idea. Obviously, we have millions and millions of tires that need to have something done with them. But again, the question is out for what's in that recycled rubber. And again, there are different. We've seen recycled rubbers that really have done a great job of encapsulating that crumbled tire, and we don't really see a lot of available 6 ppd quinone. And then we have other products where we do see it. So again, I think the take-home message here is that it's exciting because we're in this discovery period, and we're able to quantitate effectively with isotopes, but really it's sort of taking a shot in the dark on where we find these things. Let's look at, so being here in Northern California, we brought this method up really when we were starting to dive into some of the more difficult matrices in the summer. And in Northern California, there's not a whole lot of rain in the summer. In fact, we were lucky this year because we had one rainstorm in September, so that was pretty exciting. So where do we find rain if we don't have rain? Well, we go to the car wash. So took my truck through the car wash. Right when it was done, scurried back in with a couple of 50 mil centrifuge tubes, scraped a bunch of water up off the ground here, as you can see, and it was different samples depending on where I was collecting this water, but at the same time was of the essence because we had to get out before the next car got in here, and put it through our SP extraction process. And what do we get? We get some nice looking chromatography. We've got 2 ions up there for the native. This was an older one. We were actually using the D5, but you can see that having isotopes in general makes for a nice picture that even people that aren't used to looking at chromatography can say, hey, okay, it looks like you've got more than one level of confidence here, both with signal to noise and with retention time and with multiple ions. And you've got your isotope ion there, which makes quantitation possible, or more precise and accurate quantitation possible. And what do we get? We got a lot of 6 ppd quinone, and this was in different concentrations here, depending on the complexity of the sample. And you can see that we're now in the microgram per liter arena here. Again, our reporting limit, our limit of quantitation, is 2 ppt. You can see here that we are above 2 ppb for some of these car wash samples. So, and we pulled this graphic out of the published paper, and you can see that we're in that range of multi-lane roadway runoff, that 0.8 to 19 micrograms per liter. And so, these car washes are acting like a multi-lane freeway. And so we can't really comment on how the wastewater treatment plant is dealing with this water, but you can see that even if you don't have a lot of rain, you could have a significant contribution of 6-PBD quinone into more urban areas, into urban receiving waters. We were with these concentrations above the LC50, but it's not like coho salmon live in a car wash. We did repeat this actually, and I don't have that slide on here, but we did repeat this and did determine that the car washes, as they should, are using recycled water from their own car washes, and so they're actually spraying out 6-PBD quinone from these sprayers and coating your car, and then you drive on your way. I see Andrew popping on, so I'm probably running out of time here. What comes next? We are really seeing a large uptick in this method. We know that we need to support a variety of matrices. So we've got a nice little suite here with our extracted internal standard, our non-extracted internal standard, and then a backup isotope that we can use for down the road as possible PRC, performance reference compounds, for passive work. And that's it.
Thank you, Andrew, for that excellent talk on the quant results. Very fascinating. We don't have time for any questions, but there is one from the audience, so it would be appreciated if you could respond to that in the Q&A.
Yeah, you bet.
Thanks again. If you could stop sharing, please.